Assalamu alaikum and a very good morning everyone. So now in this video we are going to do an exercise related to chapter 5 for the chemical reaction engineering course. So chapter 5 is collection and analysis of rate data. So today we are going to learn the second method, which is integral method. Okay, let's see, we have one sample question. So it says that Agro-Sustainable Sdn Bhd produced a new material called green C. So it's a name of a material. Green C is light sensitive and can be converted into blue B as shown in the following equation, where from green C it can be converted into blue B. Before mass production, they need to evaluate its stability in water under the visible light irradiation in a batch reactor. The following data was recorded and tabulated as shown in Table 1. So here we have Table 1, we have the concentration profile of green C. We have several data of the time versus concentrations, various concentration by time. Okay, you are required to find the rate of reaction of green C. So we have to write the rate law, hence we need to know the reaction parameter. Okay, A, based on integral method, so here is already mentioned the direct method that we have to use. Determine the reaction order. We need to find the reaction order. In this case, we have to evaluate all the three order, which is zero order, first order, and second order, and the specific reaction rate K for this reaction. Okay, actually, even if they didn't mention, if they say based on integral method, write the rate law for green C, then basically those are the things that you have to find lah. The reaction order and also specific reaction rate K for this reaction. Okay, tabulate and plot your graph to justify your answer. So you must tabulate and plot your graph. Okay. Tabulate the data and plot the graph lah. Okay, B, determine the time. So you need to find the time for the reaction if the conversion is 85%. So you mentioned that X is equals to 0.85. And this is what kind of reactor? We have a batch reactor. Okay, so basically we can know lah which equation we have to use. All right, and then determine the volume of the batch reactor. So we have to find the volume of the batch reactor. If the initial mass of green C, we have 2 kilograms, and its molecular weight, so just now was the mass, then we have molecular weight is 890 kilogram per kilomole. Okay, so we have all of this information. Let's go one by one. What you can do actually, it's better if you try by yourself, since it's actually a very quick way to solve this problem. Try by yourself and see if you can get the same result with the one that I'm showing. Okay. All right, so let's proceed with the first question. What do you need to do? We have to find the reaction parameter. Okay, reaction rate parameter. So they ask for integral method, determine whether the reaction is zero order, first order, or second order, then find K. All right, we know that A is converted to B. A is the green C. B is the blue B lah. So the rate law, the standard rate law, since we have only one reactant, that would be minus RA is equals to KCA alpha. And we have to guess all the three. Alpha equals to 0, it means that we have to plot the graph of CA versus T. Alpha equals to 1 means we have to plot the graph of ln CA0 over CA versus time. So this one, ln CA0 over CA versus time to fulfill this equation. If alpha equals to 2, then we have to plot a graph of 1 over CA versus time. Just to take note, for alpha equals to 0 and alpha equals to 2, there is no problem. You can simply plot the graph and find whether the result follow linear equation y equals to mx plus c. However, for alpha equals to 1, ensure that your intercept, your c, must be 0. So when you draw the trend line, it must cross 0, 0. Okay, so what do? We simply tabulate. We have already the time, we have already the concentration. So for zero order, your x-axis will be time, your y-axis will be concentration. actually exactly the same information given from the table. First order, x-axis time, y-axis is ln CA naught over CA. In our case here, CA naught is 0.95, which is the concentration of A at time 0. Then you can find ln CA naught over CA. Second order, x-axis is time, y-axis is 1 over CA. We can use this CA as the value. Okay, we solve, we tabulate all the data. Then we plot the graph. We have 0 order, first order, and second order. Ensure you put the axis lah. This is just an example, so I didn't put the axis. Okay, so if we compare here, 0 order r square is equal to 0.9291. First order r square equals to 0.9999. Okay, and second order r square is equals to 0.9197. Hence, the best one is first order. We can write the red law, minus RA is equals to KCA to the power of 1, and our K will be the slope. So here our slope is 0.1973, approximately 0.2. So we can simplify is minus RA equals to 0.2 CA. Okay, we have done with the first question. Let's go to the second question. Determine the time for the reaction if the conversion is 85%. Okay, so x is equal to 0.5. What is time? Sorry. What is the time? So this is a batch reactor. So we write back the equation for batch reactor. So design equation for batch reactor, time is equals to NA naught integration of x to 0 or 1 over minus RA times volume dx. We know that CA naught is equals to NA naught over V, since V is always equals to V naught, as it's a batch reactor constant volume. Hence, we can actually simplify this equation. N naught over V is equals to CA naught. So we have T equals to CA naught integration of x to 0 or 1 over minus RA dx. Just now we have already solved the red law. Minus RA equals to 0.2 CA. And CA is equals to CA naught 1 minus x, since it's a liquid reaction. So we put this CA term in red law equation. We has minus RA equals to 0.2 CA naught 1 minus x. Okay, put into the design equation, we got time equals to CA naught integration of x to 0, 1 over minus RA, which is 0.2 CA naught 1 minus x dx. We can remove CA naught here and here. So we have simplified into T equals to x integration of x to 0, 1 over 0.2, 1 minus x dx. Take 0.2 outside since it is only a constant. So we have T equals to 1 over 0.2, integration of the rest. So integration of 1 over 1 minus x to dx, we got ln from x to 0 lah. So we got ln, okay, T is equals to 1 over 0.2 ln 1 over 1 minus x. The question mentioned that x is equals to 0.8. We can simply put into the equation. We got T is equals to 1 over 0.2 ln 1 over 1 minus 0.85. That would be time equals to 9.49 hours. Okay, settle. Question B. Now we proceed with question C. Determine the volume. Now you have to find the volume of the batch reactor. If the initial mass of green C, they give a mass which is 2 kilo, and its molecular weight is 890 kilogram per kilomole. Okay, now how do we solve it? So we know that from the previous equation, C N naught is equals to N N naught V. Okay, and if we rearrange the equation, V is equals to NA naught over CA naught. NA naught is equals to mass over molecular weight. Why did we choose this equation? This equation because mass was given and molecular weight is given. So based on mass and molecular weight, basically we can find the mole. So we can find the initial mole, which is equals to mass over molecular weight. We know molecular weight, the mass is 2 kilo. the initial mass, and the molecular weight is 890 kilogram per kilomole. We know CN0 is equals to 0.95. How do I get this? I basically got this from the table itself. Here at time 0, concentration is 0.95 molar. Okay, so molar means equals to what? 3. All right, so CN0 equals to 0.95 molar, or another unit that will be 0.95 mole per liter. The question is, what is the volume? So first we find the mole. So mole equals to mass over molecular weight. That would be 2 kilogram over 890 kilogram per kilomole. Then we get the mole is 0.002 kilomole. And we can find volume from the equation that we have rearranged just now. So N naught we change to mole unit. Why? Because C naught is in mole per liter. So 2 mole divided by the concentration, the initial concentration, which is 0.95 mole per liter. Then we get the volume of the batch reactor as 2.1 liter. Okay, we have solved the problem. Right, thank you very much everyone, and see you again in the next video.